You slide into the driver's seat, press a button, and hear a gentle, reassuring hum. It feels entirely routine. But under the hood, that quiet start is masking an environment roaring to life in violent chaos. What you're actually doing when you start a car is initiating a series of rapid-fire detonations. An engine is a heavily reinforced bomb containment chamber designed to manage thousands of explosive chemical reactions every single minute. This is the principle of internal combustion. It's a thermodynamic process where we take the chemical energy trapped inside liquid fuel, ignite it to create intense heat and an expanding fireball, and capture that outward pressure to push a heavy metal object downward. In a typical car cruising down the highway, this explosive cycle repeats dozens of times per second across multiple metal chambers, with solid steel parts flying back and forth at blinding speeds. So how exactly do engineers harness that kind of raw, destructive energy? How do you perfectly time thousands of explosions a minute to spin your wheels smoothly, all while preventing the engine from blasting itself to pieces? This technical diagram shows a cross-section of the cylinder, the primary environment where internal combustion takes place. Inside that gray cylinder housing sits the piston, the central blue component. The piston is the workhorse of the engine, absorbing the direct force of the explosions. To generate power, the engine relies on a chronological four-stroke cycle. First, the intake stroke sucks air and fuel in through the left port. Then the piston rises for the compression stroke, squeezing that mixture incredibly tight. Next is the power stroke, the explosion that physically shoves the piston downward. Finally, the exhaust stroke pushes the spent hot gases out the right port, so the cycle can restart. But a piston only moves in a straight line, up and down. To actually propel a car forward, we need rotational motion. Attached to the bottom of the piston is a connecting rod, which links down to a circular assembly called the crankshaft. Much like your leg pushing a bicycle pedal, the rod translates the piston's downward plunge into a continuous spinning force. In a standard multi-cylinder engine, a single continuous crankshaft runs along the bottom of the block, connecting to 4, 6, or even 8 pistons at once. It collects the isolated kicks of energy from every single cylinder and consolidates them into one massive, unified rotational output. That rotating crankshaft provides incredible raw muscle, but raw muscle is completely useless and highly dangerous if it doesn't know exactly when to flex. The engine needs a brain to dictate when to breathe in and when to spark the fuel. That brain is a component called the camshaft. Its specific job is to dictate the engine's breathing, physically pushing the intake and exhaust valves open and letting them snap closed at the precise millisecond they're needed. Because the four-stroke cycle requires the valves to open only once for every 2 passes of the piston, the engine operates on a strict mathematical requirement. The larger camshaft gear at the top must rotate at exactly half the speed of the smaller crankshaft gear below it, a perfect 2-to-1 ratio. To enforce this mathematical law in the physical world, engineers link the two components together using a high-tension timing belt or a heavy-duty metal chain. This grips the teeth of both gears, locking their rotational speeds together. The stakes for maintaining this connection are incredibly high. If a timing belt snaps while you're driving, the camshaft stops, but the crankshaft keeps spinning. Heavy metal valves are left hanging open right in the path of the fast-moving pistons, and they crash into each other, destroying the engine from the inside out. Every revolution of the engine depends on this flawless synchronization. Without it, the precise geometry that allows for combustion becomes a series of high-speed collisions. While this basic timing sequence applies to most internal combustion vehicles, engineers have developed 2 distinct ways to actually ignite the fuel. Looking back at this diagram of an SI, or spark ignition engine, you'll see a green spark plug sitting at the very top of the chamber. This electrical arc is what triggers the explosion in everyday petrol cars. Diesel engines take a different approach. This diagram shows a CI, or compression ignition system. Notice the top component here is a fuel injector, and there is no spark plug at all. Instead, the piston squeezes the incoming air so tightly that it generates enough heat to auto-ignite the fuel the moment it is sprayed in. This reference table breaks down the real-world trade-offs between the two designs. Spark ignition engines run on petrol with a lower compression ratio, providing smoother operation and quicker acceleration. Compression ignition engines run on diesel with a much higher compression ratio, resulting in superior fuel efficiency and massive heavy-duty torque. To squeeze even more power out of either system, you can add a turbocharger. Instead of wasting the hot exhaust gas, a turbo routes it out of the cylinder where it spins a turbine. That spinning motion operates a compressor that sucks in outside air and crams extra oxygen directly back into the cylinder, allowing for a larger explosion. By tweaking how the fuel catches fire and manipulating the volume of air forced inside, engineers can take this single four-stroke concept and customize it to power everything from a lightweight sports car to a massive freight locomotive. Because a piston's speed constantly varies as it travels up and down, an engine naturally wants to vibrate itself apart. To counter this, heavy metal counterweights are forged directly into the crankshaft, swinging in the opposite direction of the pistons to cancel out these destructive forces. Attached to the end of that crankshaft is a heavy disc called a flywheel. It acts as a mechanical energy bank. During the violent power stroke, the flywheel stores up rotational momentum and then releases it to keep the engine spinning through the intake, compression, and exhaust strokes when no actual power is being generated. Today, this mechanical choreography is constantly monitored and micro-adjusted. Smart onboard computers pull live data from dozens of thermal, chemical, and mechanical sensors, altering the air-fuel ratios and timing millisecond by millisecond to ensure peak efficiency. The next time you start your vehicle, you are initiating a mechanical ballet that safely translates thousands of violent explosions into forward motion. Every revolution is a testament to a century of precision engineering.